Okay, now let's do a Fourier series approximation of a square wave. Now we're going to start in Mathcad Prime. This is kind of a math scratch pad, I think you might call it. It's really easy to read and it's pretty easy to work with. It's a great way to do sort of homework-sized problems, maybe a little bigger. When you want to go to some serious number crunching, it's usually better to go to MATLAB, which we're going to do here in a minute. So you can see I've got the square wave defined here. And the way I did this, I made two vectors, xx and yy. I called them xx and yy because I thought I might want to use x and y as variables names later, and I didn't want to reassign these. So I go 0, 0, 1, 1, 2. Well, there's 0, 0, 1, 1, 2. That's in the x direction. And in the y direction, I went 0, 1, 1, 0, 0. So 0, 1, 1, 0, 0. That's a square wave. And notice I only did one cycle. I could do two if I wanted, but I only need one because I only have to integrate across one cycle. Now, if you remember, I'm going to blow this up a little bit here. There we go, so you can see it on, in case you're listening on your or watching on your phone. I can see right here. Oops, right there we go. There's the expression for a sub n. And you can see I've got it written out in two segments because there's basically two parts to this wave. There's the part where it's 1 and the part where it's 0. And it's discontinuous right there, so I have to break this up into two integrals. Well, the first integral, the f of t, is 1. You can see it right there. That's this right here. The second one is 0. That's this right here. Well, obviously, I don't need that part right there because whatever it is, I'm going to multiply it by 0, so it doesn't need to be there. You can see right here, I've redefined a, omitting that second integral because it doesn't need to be there. So I'm going to get rid of this and maybe scooch some stuff up so we can get more on the screen. Now let me just walk you through the calculations here. You can see I've got a defined right there and b defined right there. All right, in Mathcad, that arrow right there and that arrow right there are basically a symbolic evaluation. It's me telling Mathcad that I want an answer symbolically, not just numerically. Now, I haven't assigned it to anything, so this is just for information. The reason I put it in here is that the a and the b term both have a closed form solution. You can actually just evaluate this. Now, there's a problem in that there's an n in the denominator of both of them. If I ever try to make n 0, this form is going to be singular. Well, it's not really singular because sign goes to 0 while n goes to 0, and it actually evaluates to a number, not something undefined. Now here I said capital N equals 5, which is saying I want the highest index of my terms to be 5. I want basically a 5-term series. So I just defined NA to go from 0 to capital N and NB to go from 1 to capital N. The reason I went from 0 to N here and 1 to N there is because there is an A0 term. In fact, you can see it right there. There's the A0 term. Another thing to notice is that lots of these terms evaluate out to really, really tiny numbers. If you're looking at 10 to the minus 17, that's 0. There again, 10 to the minus 18, 10 to the minus 17. Those terms are 0. This is important to note because when you do a Fourier series approximation, particularly when you do it using sine and cosine terms, it's not at all uncommon to have some of the coefficients turn out to be 0. Now, since this is being evaluated numerically, it's not exactly 0, but if there's a decimal point and 17 zeros before you get to the first number, that's 0. By any practical measure, that's 0. All right, you can see right here, there's the Fourier series approximation. Here I've set n equal to 15. So that's going to be a 15-term series approximation. And let me blow this up just a little more. There we go. That looks better. So you can see in red, there's my original ideal square wave. And in blue, you can see the approximation. And you can see it's close. Now I let x go to 3 here, so you can see that the Fourier series approximation really is going to be cyclic. As you can see, the next cycle is starting there. And if I want a better approximation, well, it stands to reason I probably should put more terms in it. By the way, let's go down a little bit. Let's just go to 5 terms and see what this looks like. There's 5. There's 3. And you can see that it's starting to look an awful lot like just a single sine wave or cosine wave. And there it is right there, if n equals 1. All right, let's go back up to 10, getting better. Now, one of the problems with a Fourier series approximation is that it's really bad at turning corners. To turn a corner there, that's really hard to do with sines and cosines. You need a lot of terms. In fact, you need an infinite number of them. So let's start bumping this up. There's 20. Let's go to 30. Let's go to 40. That's taking a little time to calculate. Well, let's keep going. Let's go to 50, and then we'll quit here. Now, see this overshoot right there and right there? This is never going to go away. This is always going to be there, almost no matter how many terms I get, because it takes an infinite number of terms to exactly reproduce the original signal. This is called Gibbs phenomenon. What's going on here is we're trying to get sines and cosines to turn a hard 90-degree corner, and they don't want to do it. It's a very poor function to try to do that with. But you can see it's working, and it's really working pretty well. Now, can we do the same thing using complex exponentials? You bet. Let's try it. So here's the same calculation, only now I'm using the complex form of the Fourier series, not the sines and cosines. And you can see it's working reasonably well. I've spot checked a couple of my coefficients. C0 is 0.5. There's C1, C2, and you can see that one really is 0. That's 10 to the minus 17, 10 to the minus 18 there. And I've got it set up right now so that n equals 15. This is an n equal 15 approximation. And the other thing you can see here is I'm plotting the absolute value. Let's go to a larger number of terms. You can see that the Gibbs phenomenon is still there, right there and right here. It looks a little different since what I'm plotting is the absolute value, but the effect is still there. And you can see that as n gets bigger and bigger, we're going to have a better and better approximation to that ideal square wave. There's 100. Now, if there's a problem with Mathcad, it's probably not very good at grinding out large calculations. You can see it was fairly slow there. Now, it's possible that I could change the programming and get it to run faster. But there we have it. That's really pretty good. I'll stop there. Let's move on now to MATLAB, now that we know what the right answer is supposed to look like, and we can spot check it. All right, now let's do that same calculation in MATLAB. Now you can see this looks a lot denser and a lot harder to read, but it works just fine. As I said, MATLAB is a great number crunching language and is very scalable. You can do very large calculations in MATLAB that you probably can't do easily in Mathcad. Mathcad is more for homework-sized problems most of the time, unless you go to some fairly sophisticated programming. So this may look like there's a lot of text here. Let me walk you through it, and you'll see there's actually not that much to it. So the first thing I did is I made a comment here, right? And so one of the nice little things about MATLAB is if I type help SQ wave, which is the name of my file, what it'll spit back to the command window is the first comments. If I do that, there it is. This will help. This makes a complex Fourier approximation to a square wave. I could actually put another line in there if I wanted. N equals order of the approximation. Whoops. So I can even put a line in there to say, here's what the input variable means. Let's go down and try this again. Again, the name of the function is SQ wave. So I'll just press the up arrow and pull that back. Now I get that. Now notice it didn't clear the screen because that command comes later. Putting these comments in your code is really good practice. It helps you keep track of your work, and it also helps other people read your code. Now, kind of a guideline I discovered is that when you write your code, you're going to tell yourself, oh yeah, I'll remember this. Once a couple weeks are going to have gone by since you wrote the code, you're going to find out, well, I don't quite remember what I was doing here. After somewhere between 4 and 6 weeks, that code might as well have been written by somebody else because you're not going to remember any of it. Well, at least I can't. If you can, good for you, but I bet you can't. I've heard guidelines along the lines of 2/3 of your code ought to be comments. That seems a little much, but that's certainly not a bad idea. Adding comments makes your code easier to read, and it doesn't slow it down any at all. When MATLAB goes to run code, the first thing it does is throws away all the comments. So putting 10 lines of comments does not affect how fast your code runs. So let's clear the screen here, clear the command window. So I've got the CLC command in there as usual, and right there's where I'm defining the square wave, just exactly as I did in Mathcad. Now the next line here, right there, I've written out an expression as an anonymous function for C sub n. Well, the reason I can do that is offline I went ahead and figured out what that was, evaluated that integral. And I happened to do it in Mathcad just because it was easier to look at. Now Mathcad and MATLAB use the same symbolic processor. It's called MuPad. So you can have confidence you're going to get the same answer in one as you do in the other, although ideally it shouldn't matter what symbolic processor you're using, you should get the same answer. So I wrote this out in Mathcad, and if there's a problem, it's right there. There's an n in the denominator, as we saw before. So C is going to work out great until I try to put in 0 for n, and it's going to barf. See, not happy at all. Well, C, when you evaluate it, does converge to a number. It's not undefined. That's because of the numerator. Now, this isn't a proof, but a demonstration. N doesn't have to be an integer here. There's nothing about this expression that requires n to be an integer. We understand it to be, but the mathematics doesn't know about that. So what I can do is I can put a small number in for n, and I get my 0.5 real and some small imaginary part. Well, what if I make C smaller? I approach 0. That keeps getting smaller and smaller, and eventually it'll get so small that it doesn't really report it anymore. Give it one more 0. There we go. It's too small to even report. I'll leave it right there. Now what happens if I approach 0 from the other side? I get the same thing. So we can have confidence that C sub 0 really is 0.5. And it should be. That C0 term is basically a DC offset. And it makes sense that there should be an offset to the sine waves we use to approximate the square wave. Okay, so here we are back. I'll explain that. The next couple of lines are just bookkeeping. I'm going to go to 3 seconds, that's t final, n sub t, n underscore t, that's the number of points I'm going to use to make the plot, and dt is just the time step. As before, I've got t equals 2 and omega is 2 pi over t. I'm just using a w instead of omega because MATLAB doesn't know what Greek characters are. So next thing I did is I made a time vector. I did this up outside the loop just to speed things up. And right there, I've got a command that I've commented out. I'll tell you about that here in a second. So here's the real meat of the routine. I'm stepping forward in time in an outside loop, and in the inside loop, I'm adding up all the terms in the series for a given time. Now, the little game I had to play here is in adding up the series, I added up the positive ends and the negative ends separately. And right there, I started y, which is going to be the variable I assign the summation to. I made that 0.5 because that's the DC offset. And notice my loop doesn't go from minus little n to plus little n through 0. It goes from 1 to big N. So I've got positive ends there and negative ends there. And I'm skipping 0 because if I try to evaluate it, it's going to be undefined. I'm going to be trying to divide by 0. And there it is right there. I start with that. And the last thing I do is just take the absolute value of y. And then when I'm done, I'm just plotting x, x, y, y, which is the ideal, and then my complex Fourier series approximation. So there it is. I'm going to get rid of some of the space here, make this a little more compact on the screen, and maybe I'll pull that down a little bit so we can see the whole thing. There we go. Now, if you go over here, you're going to see that there's some warnings. One of the interesting ones I just found, actually, is I had this originally written out this way, where I is understood to be the square root of -1. In MATLAB, unless you redefine I, it's always the square root of -1. Well, down here, see that M? That was originally an I when I wrote it out the first time, and of course it didn't work. So I changed I to M, and it did work, and at the same time, I got this warning. For improved robustness, consider replacing I and J by one I, because I and J get used for indices a lot in programming, but one I only has one meaning. That is the square root of -1. So you click there and click there, and that solves my problems. Now, I haven't been brave enough to go back and turn that M into an I. It just doesn't seem like a good use of time right now. There's one warning left right there. On line 17, I'm changing the length of this vector SQ for square wave. Every time I go through here, it gets bigger. Now, I just noticed one syntax problem here. That shouldn't be a colon, that should be a comma. If you don't give the zeros command 2 dimensions, it makes a matrix the size of whatever dimension you gave it. I want SQ to be a vector, not a matrix, so that should be a comma, not a full colon. And I could do this n sub t plus 1 comma 1 if I wanted to, depending on whether I want to make a row or a column vector. It doesn't really matter in this case. So let's turn that back on and notice that all my warnings went away, and I've got no warnings found. So let's try this now. Let's just start with n equal 5. So the summation goes from -5 to 5, including 0. There it is, and there's my plot. That looks pretty good. There. Let's make those lines a little bigger so maybe you can see them better. Go ahead and get the property inspector going here. Let's make a line width of 2 so it'll be really easy to see. And this one, should have left the property inspector open, sorry. Let's make this one 1. And unselect that. So there we go. That's what it looks like for n equals 5. Well, let's go farther. Let's make it 50. Okay, you can see, hang on, let me do this again. And you can see the Gibbs phenomenon right there, but that's looking more and more like a square wave. Well, since this runs so fast, let's go crazy here. And again, it's looking more and more and more like a square wave. Gibbs phenomenon is still there, though. And I can keep going as long as I want. At this point, it's going to run. Maybe. There it is. Okay, at this point, my problem right now is that the features I want to see right over here in these corners, I probably can't resolve with only 1,000 steps in time. So if I want to really examine what's going on at those corners, I probably need to set the number of plotting points at more than 1,000. But you can see at 500 terms, or n equal 500, capital N equal 500, we get a very, very good square wave here, and it's clearly periodic. So there you go. Here it is in MATLAB. Works really well, efficient, runs fast, partly because I did that symbolically. One of the reasons the Mathcad file was running so slow is because I was making it evaluate it, see every time I needed one. I was actually making it do the integral. And by defining it symbolically in the MATLAB file, I skipped that step. So that's a lot of number crunching that doesn't need to take place, a lot of clock cycles that don't need to happen. So hope this helps, and we'll talk to you next time.